Hello everyone, my name is Ashod Nakashian, also known as Ash, and I will be talking about the challenges of designing and testing the async save and upload feature in Collabora Online. Briefly, Collabora Online is a web application that is a platform that allows users to collaboratively edit documents, presentations, spreadsheets, and behind the scenes, it has a server that is written in C++ that is responsible for managing the connections and handling all of the user input and ultimately rendering the results as well and saving and storing the data in the storage server. So whenever the user saves a document, from their perspective, it is a single act, but behind the scenes, first of all, we have to save the document in the format of choice to a file, and then that file is uploaded to the storage server, which is a separate server, typically in a remote machine, not necessarily on the same machine, and it will be backed by a database and other complex machinery to handle the documents and also authentication and other important details. Also, one of the features of the storage server is that it typically supports versioning. So every time that we upload a document, it gets added as a new version and the user is able to go back and restore previous versions as necessary. So that basically means that whenever the user is saving, implicitly the document is also uploaded and stored in their storage as well. The problem is that we needed to avoid having any performance issues whenever the upload stage of the saving was slow because the document was large, or indeed because there were network issues, congestion on the network to the storage, or the storage server itself might have some downtime or be slow to react and so on. So that was the main problem that we were trying to solve, but to do that we also had to separate the saving of the document to file on disk and uploading, because these are conceptually separate and independent activities, and we needed to make sure that the uploading was done in an asynchronous fashion, whereas previously it was done synchronously, blocking basically all of the user input, and that was noticeable on the UI. But we had to do all of this without introducing any new instability or issues to the product. The challenge was fundamentally in that the socket and networking layer that we were using, which was primarily based on POCO, was a blocking one, meaning it was synchronous, and so we couldn't change that easily. And POCO had its limitations that we were already struggling with anyway. So we wanted to be able to change the socket, but that meant that we also had to refactor and redesign a lot of the code, because a lot of the internal structure was somewhat coupled by this critical stage of the document saving. Now, whatever solution we came up with had to also support all of the security measures, specifically SSL in the different flavors, and it also had to support all of the different protocol level features such as chunk transfers, redirections, and of course all sorts of error conditions and edge cases. Any major change, such as a fundamental networking layer or a common piece of the code, brings a lot of risks with it. The most obvious one is that you introduce a lot of instability because of large amount of refactoring, a large amount of new code, and we had to write a certain amount of new code just to support the HTTP logic, which we did not have any code in our code base for. As I said, we were using primarily Poco, and that was how we handled all of the HTTP protocol details. Another thing is that whenever we saved, we didn't necessarily immediately upload. Saving and uploading could have happened as part of more complex operations, such as renaming or converting the document, or conflict resolution whenever there were multiple document versions saved behind the scenes from a different server or a different connection. So we had to deal with all of these scenarios without breaking them, whilst modifying the internal design from a synchronous blocking model to an asynchronous model. The solution that we came up with, unsurprisingly, leveraged a lot of the networking level code that we already had, all of the infrastructure that we had built to act as a server to accept connections from our clients and to be able to handle all of the communication on it. Specifically, since all of the protocol is done over WebSocket, we had already all of the WebSocket logic written, and the low-level socket handling was done via directly using Linux system calls, and indeed wherever the system calls that we were doing were POSIX, that was translatable to other platforms as well. And on top of that, we had the SSL layer that provided all of the security measures, and we had the WebSockets as the protocol or the application level protocol logic. What we were missing was the HTTP logic to act as a client instead of a server. So we needed to support uploading by basically acting as a client, connecting to the storage server using a certain URL, and that URL could be SSL or non-SSL, and we had to comply with whichever it was, and basically act as a client HTTP doing the upload through the regular HTTP protocol verbs. Now, that's on the socket level, and we were missing the HTTP logic. But we also had to make sure that whatever approach we took did not necessitate a new approach to handling the asynchronous socket communication, and indeed that it did not require a large amount of refactoring. Ideally, it had to be something that would be a drop-in replacement with only the logic around handling the state of the socket itself. Whenever it was done, there would be a certain event fired. Whenever there was an error, that event would fire and the error code would be propagated, and so on. This is a very simplified high-level view of the design that we had already for handling all of the client connections in the documents. The server thread on the left is the external facing thread that is responsible for accepting incoming connections from the clients, and once the socket is accepted, and we knew that this was for a specific document, and we made sure that this client passes all the necessary security checks on that level, we passed it to the document. And within the document, we had only one polling thread, and that meant that we didn't really use a lot of system resources, and we had one poll call to handle all of the client sockets to do the communication both ways. Basically, it handled the incoming data as well as outgoing data. Within the document polling thread, we didn't have any other responsibilities or any other threads, so this seemed like the ideal place to add the client socket that did the asynchronous uploading, basically leveraging the infrastructure that we already had by just adding another socket to the list, and that socket was a special one. It was a reusable one, and all it did was basically upload the document to the storage and nothing else. Once we are done with all of these changes, the biggest challenge then becomes testing and vetting that the solution is viable, it meets all of our needs, and it also is extremely stable and reliable. Primarily, we started this project on very solid grounds. We already had a large number of tests, both unit tests and integration tests, and that means that we had tests that exercise the C++ code on the back end, but we also have a very large set of tests that exercise user interaction and input on the front end, on the browser side, and that triggers saving and verifying that the data that was entered was in fact saved after reloading the document or closing it and renaming it, etc. So we started with that battery of tests as our safety net in terms of finding regression, and we built on top of that by adding a large number of tests that exercised all of the new HTTP code, specifically all of the data parsing, all of the edge cases, the error conditions, and we also added round-trip server tests that opened a client-side connection, a server-side connection, and sent and received data back and forth, and that was the foundation that was used for fuzzing, which we made sure that would basically give us a very, very high coverage in terms of data and the code paths that are taken and the internal states that were exercised and triggered, and we run the fuzzers continuously to make sure that we are able to catch any edge cases or regressions, and by that we ensure that we have a very solid piece of code. We also made sure that the new tests that we've added caught new cases that were basically the result of changing the internal structure and the logic of doing the saves asynchronously. Meaning that with the synchronous approach, we basically didn't have a possibility of issuing multiple uploads at the same time. But now that we have it as an asynchronous process, we are able to issue multiple uploads. Just as an example, so we had to catch that and handle it gracefully and postpone the uploading. However, the user could still issue multiple save operations from the front end. So again, we had to manage the multiple saves. We had to make sure that we are able to track the state of the saving and uploading, and in that scope we also had to handle failures of uploading or saving as well, and retry whatever failed on the first opportunity, so that we make sure that we recover gracefully and we have a transparent save and upload operation happening in the background even when there are failures. Ultimately, the results that we achieved were very reliable code that was homogeneous. Fundamentally, it leveraged the infrastructure that we had already invested a lot of effort and a lot of time to tune and debug and make sure that it is performant. So we ultimately reduced the footprint of our code by eliminating an external library, which was Poco in that case, and we made sure that the code is now working in the same way for both client-facing connections as well as the upload connection, and all of that is happening without using any extra resources. The upload socket is reused, so again, it's very efficient, and we only have one to deal with because we don't need more than one connection to the storage for a given document. And ultimately the UI performance improved significantly. There are no visible pauses whenever a large document is being uploaded, or there are any network issues or slow storage server or anything like that, because we are able to process and handle any incoming user input while we are uploading the document, the last version that was saved. Once the saving and uploading is done in the background, we do notice that there has been a modification, and within a certain timeout that is configurable, we are able to save and upload again. And this repeats as many times as necessary. And of course, the user can also invoke a save operation at any time as necessary. We guaranteed basically that the tests and the approach that we took did not introduce more code or more changes than was necessary, and that was also one of the key goals that we had. Basically, when we replaced the existing code, we had a very similar code in terms of the interface, but the implementation was completely different. It had to assume, for example, that the socket was going to be added to our socket pole, and the plumbing was going to be done in exactly the same way that we were doing. But the code that created the socket passed the certificates for the SSL, and indeed most of the function calls for setting the headers or doing any of the HTTP logic, they were designed to be very, very similar to the existing code, so that we don't need to refactor basically what would have been cosmetic differences. And with that, we were able to both have a very maintainable code base and guarantee better performance and stability for our clients. And with that, I am more than happy to take questions. Thank you for listening and for your time.